Right, hello and welcome to the Daily Space for Tuesday, June 19th of 2018. I am your host, Dr. Andres Plazas. Unfortunately, Dr. Pamela Gay couldn't come today. She's not feeling well, but she says hi to everyone. Hopefully she will feel better tomorrow. But as always, we're going to bring you a roundup of today's news from space and astronomy. And today I'm going to talk about two topics. One of them has to do with black holes, and the other one with exoplanets. We all like exoplanets. I like exoplanets. I'm not an expert in exoplanets, but I could have studied that if I had to come back to grad school. I think it's cool. Anyhow, but we're going to start talking about black holes first. So the first news of today, so it's telling us that so we know that there are different types of black holes in the universe. So some of them they're massive stars that create a stellar mass, what we call a stellar mass black holes when they die, and the mass of these black holes could be up to 100 times the mass of the sun. And there are other types of black holes that live at the center of galaxies, and we call them supermassive black holes, and we call them like that because these type of black holes can have up to billion times the mass of the sun. So then what about in between, right? We're talking from 100 to 1 billion. So of course, we believe that there are another type of black holes that are called intermediate mass black holes. But they turn out to be very difficult to find. And this story today is talking about one candidate of an intermediate mass black hole. So some people believe that these intermediate mass black holes are the seeds that will eventually grow to become, for example, a supermassive black holes. But they are very elusive. So in this particular story, the researchers have used X-ray data from a space observatory from the European Space Agency, the Newton XMM Newton X-ray Space Observatory, as well as observatory by NASA, the Chandra X-ray Observatory, and archival data from other ground-based telescope. They have used this type of data to detect a very large flare of radiation in the outskirts of a distant galaxy. And this flare of radiation is a consequence of the star passing by close to the black hole, and then the star was subsequently devoured. So then that triggered this activity that could be seen then with the X-ray detectors. So some of the scientists of the study, some of them from the University of New Hampshire in the United States, they say that this type of black hole hasn't been spotted so clearly before. And they say a few candidates have been found, sorry, but as I said, they're very rare to find, and they're very sought after. We're really looking for this type of black holes to fill in the picture of the black hole family. And just as a reminder, for example, the black holes detected by LIGO through gravitation by merging and then we detect their gravitational wave signals there. If I remember properly, their final mass is about less than 100 solar mass. So this would fall into the category of stellar black holes, as I was telling. So this type of black holes, they could form in different waves, these intermediate mass black holes. So one way that people think that they form is when you have a globular cluster, when you have a dense cluster, then you have a merger of stars that are going just run away and they just actually collide, and they actually become into one of these intermediate mass black holes. But then by the time that these type of black holes have formed, then in the globular clusters you don't have more gas because all the stars have been formed already. So the black holes are not going to be consuming any more material, and they're not going to grow more. So there's no more radiation from that to emit. So it's very hard for us to find them because of course by definition a black hole you don't see it, right? Well, however, there is a different technique that they have used in this study, and as I mentioned before, you can actually also wait for a star to pass close to the black hole, and then it becomes disrupted, and this activates the black hole's appetite, so to speak, and then it emits a flare that we can observe. So actually, the researchers, they searched through archival data, went to the archives of the Newton Observatory, the European Space Agency Newton Observatory, and they found a galaxy about 740 million light years away. And this data was taken in about 2006, 2009, and they also looked at data, archival data from other ground-based telescopes, and they actually compared the brightnesses and the different characteristics of the galaxy and the outskirts of the galaxy to see that something has changed, right? So, for example, one of the images appeared far bluer and brighter in one of the images that it had just appeared a few years previously. And then they said that by comparing the data, they could figure out, they could infer that the star at the outskirt of this galaxy was slightly disrupted about in 2003 in our time, and then it produced a burst of energy that decayed over the following 10 years or so. Yeah, well, this is a very interesting news, as I said, because we don't have a lot of information about this this intermediate type of black holes. And one interesting analogy that one of the researchers uses when talking to the press is like, for example, it's like if we had an ancient civilization observe us, and they would only see the picture of an elderly person, of a grandfather just leaving their kids at school. And then they're what, right? Then the model would tell you, well, maybe surely there must be something in between. So this is exactly what we're trying to find. We're trying to find this type of black holes whose masses are about 1,000 to 100,000 solar masses, as opposed to the stellar mass black holes that are up to 100 or hundreds, or the supermassive black holes that could be up to 1 billion of solar masses. So yes, that was the first story that I wanted to talk about today, and then I'm gonna move over to the next story, and then at the end I'm gonna check the chat and see if we have some comments from you guys. But then I also saw this story in the press release about a new way of finding exoplanets just by looking at molecules in the atmosphere of the exoplanet. So, well, an international team of astronomers from the University of Geneva, they actually submitted this study to the Astronomical Journal. And one interesting thing is that this study was published yesterday, I think, was accepted yesterday. And then I went out and looked out for the paper. And then I found it in the archive. I've mentioned the archive here previously. And the paper originally appeared in February of 2018. But the press release appeared only until yesterday. So the moral of the story is like, of course, anybody can publish on the archive. But usually there is the assumption that you have submitted your work to be peer reviewed, right? That's how science works nowadays, by consensus. And yeah, it's just interesting that you won't have a press release until it has been actually peer reviewed, which is good. I used to work at JPL a few months ago, for a few years, it's a NASA center managed by Caltech, and they had the same policy. We cannot publish anything that hasn't been peer-reviewed if it only has appeared on the archive. On the other hand, it's great that all the knowledge is available on the archive and is not behind a paywall. But anyhow, that was just sidetracking a little bit. But focusing again around the story. So one of the problems that we have when we're trying to find exoplanets, it's that of course they're gonna be revolving a star around a star, and the star is too bright. So usually it's too dazzling. You cannot see it. You cannot image the exoplanet. It's very hard, just because they're far away and it's bright. So, but in this particular story, these researchers came up with a new idea, and then they said, okay, maybe we can detect certain molecules that are present in the planet atmosphere, and then we can make it visible in that way. If we assume, no, provided that these same molecules do not are absent from the star. So if you can think of a certain set of molecules like methane, water, which are the ones they're going to talk about here in the study, you can look for the traces of those molecules in the stars, in the atmosphere of the star, of the planet. And if those molecules are absent from the star, then you have a method to say, oh, maybe there is a planet right there. So the researchers said, okay, if we focus on the molecules that are present only on the studied exoplanet and are absent from the star, from the host star, the technique would effectively erase the star, leaving only the exoplanet. And then in order to take this technique, they use again archival data from an instrument. It's called Symphony. It's an instrument mounted in the very large telescope of the European Space Observatory. It's an instrument that for every pixel you get a spectrum of whatever you're imaging, of your line of sight. It's an integral field spectrograph, and I've talked about this in the past. So the star that they chose is called Beta Pictoris, and it has a giant planet that is orbiting around it that is called Beta Pictoris b. So just the letter B. So as I said, every pixel of these images, they have the spectrum of the galaxies, and then the astronomers they compare the spectrum containing the pixel with the spectrum corresponding to a given molecule. So first, so I went and looked at the paper, and they actually create a template for the spectrum of the star. What do we believe the spectrum of the star looks like? And then you can subtract that template from the data of your pixel, and then if your model is good, then you're going to end up with residuals that do not have the star. So that's good. And then at the same time, you have templates for a certain type of molecule. So here they chose 4 molecules. They use water vapor. They use carbon monoxide, methane, and ammonia. And then if you have a template for those 4 components, for those 4 molecules, you can do something that is called cross correlation, which is just basically comparing, like doing a one-by-one comparison of the spectrum of the residuals that do not have the star from the real data and the molecules. And then you're going to see a match. If you see that when you do this cross correlation, then you see like a peak in your signal, that means that is like a positive correlation. So it's gonna tell you that you have that type of molecule in the planet atmosphere. So so if you guys want to take a look at the pictures that I have here, these are 2 pictures from the papers. So let's take a look first at the upper left picture, which is just basically a map. It's a physical a map of the cross correlation. So the colors are telling you that if you have white colors, then you have a positive correlation. If you have dark colors, you don't have a lot of correlation. So the lower, I'm looking again at this upper left image, and if you look at the lower 2 squares, the lower 2 panels, the red one corresponds to carbon monoxide, and the one on the upper right, the blue one, corresponds to water vapor, to H2O, H2. H2O. Sorry. Well, anyhow, but if you squint a little bit, well, actually you can see it very well. You see a white dot right here, almost at the center, and that's the planet actually. And in every one of these four panels, they put a star, an artificial star by hand, because of course in the data, the actual star didn't show up, which is good. It's telling us that the star doesn't have these four molecules. But then we see that in the lower panels, the planet doesn't appear. So it's already telling us that this planet has CO and H2O. So it has carbon monoxide and it has water, but it doesn't have methane or ammonia. So that's great because it's already allowing us first to detect the planet, and then it's telling us what the elements of the surface of the planet are. And there's another well, there's two more things that I want to tell you. So if you look at the other picture here, this is in the lower right part. I just wanted to show what these correlation techniques look like, and it's just basically this peak that I was talking you about. So basically you can see in this plot, in the y-axis is just a measurement of the correlations, and the y-axis is a measurement of the wavelength. If you want to talk about it, it's actually velocity, radial velocity, but is correlated to the width of the spectrum. But let's not get into the details. The point is that you see a peak in the two curves that correspond to ammonia. I'm sorry, to carbon monoxide and to water vapor. But you don't see anything. You only see noise in the other two spectra. So I thought it was cool just to look at that and to have a feeling on how this cross correlation could work. And that's exactly how they find gravitational waves. Like from general relativity, you have a template of what the signal should look like, and then you have like hundreds of thousands of those templates, and you compare to the data, and then you do a cross correlation, and then when you see the peak, that's your signal. That's your gravitational wave signal. But anyhow, coming back to our story and to finalize, there is one more piece of information that you can tell from this, and it's telling you about the temperature of the star, and because so we know that the star, you couldn't see it in any of the four. You couldn't find these four molecules in any of the star because this is a star that is extremely hot and it has a high temperature, and these four molecules are destroyed. So it's also this is data is also telling you information about the temperature of the planet. Because the fact that the astronomers, they cannot find in this planet, in Beta Pictoris b, they cannot find methane or ammonia, is consistent with a temperature estimate of about 1,700 degrees Celsius for this planet. You can estimate the temperature with other techniques, but it's consistent with that because this temperature is already telling us it's a temperature that is too high for this type of molecules to exist. So yes, the researchers, they say that this is a technique that is only in its infancy, and but it's a way that it should change the way that the planets and their atmospheres are characterized. And I believe that in the paper they also calculate with, they also compare with standard techniques of finding exoplanets about stars. One of them is called, I think, atmospheric differential imaging or something like that. But anyhow, the point is that in the paper they see how using the regular techniques the planet would have been missed. But using this new technique, they're illustrating that this new technique works with this archival data. And of course, now you need to test it with other data, and then it's going to be different, but it's good to have a new tool that gives us all this information about, first, about the existence of exoplanets, and secondly, about their composition and even their temperature. And okay, that's what I have for today, just these two stories. But let me know if you guys have any questions. In game. Okay. Okay, I'm looking at your comments. I'm going up. How do you prefer we address you? You can just call me Andres. Yeah, thank you. Yeah. Ta-da, ta-da. Yeah, I usually just look at the comments at the end. So I'm going back and see if you guys had some comments. Well, somebody says I once called Dr. Gay Pam. Uh, yeah, I think the good thing regarding this, just to be safe, just call people Dr. last name or Dr. whatever, and then ask if it's okay. And in particular, I mean, in general, yeah, that's the general rule of thumb. And in the news, I saw yesterday how the president of France was scolding a teenager because he just called him like, "Hey, what's up, man?" And he was like, "Well, you should be more respectful." But anyhow, I'm just going down the comments. Mm, yes, black holes are pretty cool. Yeah. Okay. I love that such discoveries are often from older data. So much to discovering hidden data treasures. That's true. And I also love that. I also love that you have all this archival data. And even a lot of this data is actually public. And like even you guys could go to these websites and download the data. And yeah, granted, I mean, you sometimes you need to know this fancy technique or this other technique, but there are some nice visualization that you could do, and sometimes you can find tutorials online. For example, for the Sloan Digital Sky Survey, if you go to their website, and then you can see how you can use their actual data to actually find something that scientists originally may have missed or didn't have the time. Nowadays, one of the things that we have is that we have a lot of data, which is good, and sometimes we don't have the person power or we don't have the people to try to figure it out, and that's why we have citizen science. And as you know, guys, here at CosmoQuest, if you go to our website, you can help us map the moon and Mars and do a lot of cool citizen science projects because there's a lot of data that's sitting there in the archives, in the not the archive, in some archive from the Hubble Space Telescope somewhere that then people can come up and dig it up. Okay, so you guys are very excited about black holes. Me too. These molecules are they emission lines in the spectra of the parent stars? So yeah, so these molecules, I think I don't know why they choose these four molecules because I think they're more likely to be in a planet. But yes, when you look at a pixel from an integral field spectrograph, then you have as I said, you have the data from everything that comes from the light outside. You have noise, you have even like data from telluric activity from the star. You have the spectra of the star itself. But we know about the star formation due to their brightness and the temperature. We can more or less tell what their spectra should look like, what their emission spectra should look like. And then you can subtract that spectra, and then you have the template from these four molecules, and then you can do the cross correlation to try to look for this type of particular elements. And I guess you could also pick some other elements, but the researchers that are in this field and they are the experts, and these four elements are probably some of the likely or the ones that we're looking for. No, I want to know if there's water, for example. As important water as we have talked before, it would be important to know if there's water vapor in the atmosphere, if there's methane and other type of molecules, right? Um, Midges are attracted to CO2. There were lots at the England game. I don't know whether the midge is from the Volvo. Oh, the insects. That is correct. Yes. That's an interesting remark. Another interesting thing is that ticks are attracted to CO2, and then researchers, I happen to know a tick researcher, and they usually use dry ice to attract um, ticks. And actually, that's how ticks find you when in the summer. They quest for CO2. But anyhow, I like that here we can talk about a lot of topics. You guys are very curious. Ta-da. Okay, some bitches bite, whatever they call. I am surprised that Japan won against Colombia this morning. I'm sad. I'm from Colombia, but I hope we'll do better next time. That's football for you. um, so Larry says, are they absorption lines or are they emission lines? That's a good point. I thought it was emission lines, but to be honest, I'm not completely sure. I should check that out. So it shouldn't be hard to know. Um, well, I'm trying to remember because it could sometimes, yeah, it's not that hard. I knew this at some point because the way it works is just by quantum mechanics. But that sometimes if you have your states of your electrons around the nuclei, and for example, if a particular state is excited by a photon and then it goes up to a higher energy state, but then after some time it comes back and then produces an emission. But that sometimes you have a particular photon that absorbs at a particular frequency and then you don't have that extra decay again and then you just have an absorption line. So the short answer is I don't know right now. I'm sorry for that. So we should I'm gonna check that out and I should know. Okay, guys. I think that's it for today. Well, thank you so much for staying and for commenting. This has been the Daily Space. It's a production of CosmoQuest, as created by the Astronomical Society of the Pacific. So give us a follow if you can, or subscribe, even better. So, and yes, tomorrow hopefully Pamela will feel better. So yes, we'll see. Okay, bye bye everyone.